All right, so let me remind you of the definition of infinite limits that we just gave in a previous lecture, and then we're going to do a couple of examples where we're going to use these definitions. So we say that a sequence converges to infinity if for any prescribed positive number there exists a threshold value of an index capital N, such that if n is bigger than capital N, then Sn is greater than capital M. So Sn gets arbitrarily big when n is large. And there is a symmetric definition for limit equal to minus infinity, except that in this case you take an arbitrary negative number, and there should exist a threshold index such that Sn will be lower than this arbitrary negative number as long as n is sufficiently big or bigger than capital N. And so this would be a definition of limit equal to the negative infinity. All right, so let's do several examples. Example number one. Let's take a limit as n goes to infinity of, let's say, n 2n squared plus 3. And of course, I expect that this sequence is going to go to infinity because 2n squared plus 3 grows without bound. So I want to prove this by using a definition of a limit. And again, first let's look at the idea that we are supposed to use. We choose capital M greater than 0. And what we want 2n squared plus 3 to be bigger than this capital M. All right, so how can I make 2n squared plus 3 bigger than capital M? Well, I can solve this inequality for n. So the inequality is going to be equivalent to 2n squared being bigger than m minus 3. In this case, actually, what is important for the definition of the limit is that I should be able to make my expression bigger than any m. So that means that I can choose not m bigger than 0, but m bigger than 3, and that should be sufficient. So let's take m greater than 3, and it will be clear in a second why. So m minus 3 now is going to be a positive number. So n squared then is greater than a positive number n minus 3 divided by 2, and saying this is equivalent to saying I want n greater than square root of m minus 3 divided by 2. Okay, so then I can immediately construct the proof. So I'm going to set capital N to be this number. Suppose n is bigger than capital N, which is the same thing as saying n is greater than square root of m minus 3. Saying that, again, as usual, I'm following the chain of inequalities backward. Saying that is equivalent to saying this. That in turn is equivalent to saying that 2n squared is bigger than n minus 3. And that in turn is equivalent to saying that 2n squared plus 3 is greater than m. And that means that I'm done, right? Because I chose an arbitrary m bigger than 3. Then I was able to compute capital N. And then following the computations here, but in the reverse order, if n is bigger than capital N, then 2n squared plus 3 is bigger than capital M. So that means that I satisfy the definition of the infinite limit. Example number 2. I'll take a limit n goes to infinity. Let's say of n plus 1 over n squared minus 3. And this limit is supposed to be what? Top goes to infinity, bottom goes to infinity, so this limit is 0. So this is not an infinite limit. What about if I put n cubed up here? So now, top goes to infinity, bottom goes to infinity. This is an indeterminate form. Top goes to infinity faster than the bottom, so that means that I would expect that the limit is going to be infinity. So I want to prove that by using the definition of the infinite limit, that this is equal to infinity. Let's proceed in the same way. So we're going to choose capital M. So the limit is infinity, capital M greater than 0. Then let's see, what are we trying to do? We want to have n cubed plus 1 over n squared minus 3. We want that to be bigger than m. All right, so one thing that I could do, just like in this case, I can try to solve this inequality for m. But you see that it's not going to be very easy because then at the end of the day I have cubic powers of n, quadratic powers of m here. So if I'm going to solve this inequality, I'll have to end up solving a cubic equation, which I probably don't want to do. So then what can we try to do instead? Let's look at, so again, let's write this as an idea. What do we want to do? We want n squared plus 1 over n cubed plus 1 over n squared minus 3. We want that to be bigger than m. So if I'm able to find an expression which is smaller than this and simpler looking, then maybe the inequality is going to be easier to solve. Well, if I drop 1 from the numerator is going to be smaller, then I'm going to get something smaller than this. This is bigger than n cubed over n squared minus 3. By the way, I have to make sure that the denominator is not negative if I'm claiming this. But again, if n is large, then n squared minus 3 is positive, so I don't really need to worry about it because at the end of the day, n squared is going to be bigger than 3. So I can implicitly assume that n squared minus 3 is a positive number. So then dropping 1 will make this expression lower because it's a positive expression. But then also, if I look in the denominator, I have minus 3 in the denominator. So if I drop minus 3 from the denominator, I'm going to make the denominator bigger. And if the denominator is bigger, then the ratio is going to be smaller. So this should be larger than n cubed divided by n squared, which is in fact n, because I can cancel n squared. And now, if I request n to be greater than m, then this expression is going to be greater than m. All right, so then my proof is immediately going to follow. Suppose So I'm going to make capital M my capital N. So suppose n is bigger than capital N. From this, I can conclude that m is bigger than m, because capital N and capital M are the same thing. But if n is bigger than capital M, then I can follow the same chain of inequalities as I have over here. So in fact, I'm just going to copy them. So then this is going to be true, and I'm done, right? If n is bigger than m, then all of that, all of the stuff here still holds. So that means that my sequence, the limit of which I'm taking, is going to exceed m as long as n is bigger than capital N, which is exactly the same as m in this case. And so once again, we satisfy the definition of a limit, so the proof is done. Example number 3. Let's take a limit as n goes to infinity of maybe n squared minus n cubed, 2n squared minus n cubed, divided by n plus 6. All right, so in this case, again, this is an indeterminate form. Top goes to infinity, bottom goes to infinity. Well, bottom goes to infinity, but top actually goes to minus infinity because n cubed is going to grow faster than n squared. So bottom must be going to minus infinity because n cubed is going to be. And so minus infinity over infinity. But numerator has n cubed, denominator has n. Again, n cubed grows much faster than n. So n cubed over n will go to infinity, but with minus sign, this actually should be minus infinity. And again, I would like to prove this. So let's, we need to satisfy the definition of the limit equal to minus infinity here. And here I have to select a number capital M which is less than 0, and then find the capital N which will ensure that Sn is less than m. So let's do that. Choose any m that is smaller than 0. And then let's figure out what we need to do. So we want, once again, we want 2n squared. Let me write this here. So we want 2n squared minus n cubed over n plus 6. We want that to be less than m. Well, again, in principle, I can solve this inequality for n, but that's going to be fairly involved because it is going to be a cubic inequality, cubic in n. So then rather, I would want to simplify this expression and then solve a simplified inequality. All right, so I have 2n squared minus n cubed over n plus 6. And as usual, maybe what I want to do is to get rid of certain parts of this expression. And in this case, what I want to do is whenever I get rid of the expression, I want to make the resulting simpler guy larger than my original expression, because eventually if I find something larger than my expression and that larger thing is less than m, then the original expression is less than n. So in this case, if I, for example, now what do I need to drop from the numerator? I can try to drop minus n cubed, or I can try to drop n squared. Well, I cannot really drop minus n cubed because that's a largest term there, which is going to govern what is going to happen. So I keep the largest term, and I would like to drop 2n squared. So if I just drop it, I will have minus n cubed over n plus 6. And unfortunately, it's not going to work because 2n squared is a positive number. So if I drop the positive number from the numerator, I'm going to get the difference. Well, actually, it doesn't matter what the difference is. I'm going to make the whole expression actually more negative, right? And if I'm making it more negative, that means that I'm not going to get the inequality sign that I put here, because that inequality sign is not going to work, because without 2n squared, I'm going to get something smaller rather than bigger. So dropping 2n squared is not going to do it. What else can I do? Well, if I look at 2n squared and I try to compare it to maybe n cubed, maybe n cubed over 2. So what I actually need to do? I would need to replace the guy. Let me see what I'm actually trying to say here. I need to replace 2n squared with something larger than it, but something that would still be smaller than minus n cubed, because I have to preserve the largest term in the numerator, and I have to preserve the minus sign. So one particular choice is then to try to replace 2n squared with n cubed over 2. Is that actually always going to be true, that 2n squared is going to be larger than 2n squared, then that 2n squared is going to be smaller than n cubed over 2? Well, let's see. So is this going to be true? Not always, but certainly if I multiply both signs by 2, 4n squared less than n cubed. And if I divide everything by n, and here is a positive number. If I divide everything by n, I'm going to get 4 is less than n. So if n is greater than 4, then n cubed over 2 must be greater than 2n squared. And then I can replace 2n squared by n cubed over 2 above. And the resulting expression is going to be larger than the original expression that I had, right? Because n cubed over 2 is bigger than 2n squared. Okay, so that's fine. So if n is greater than 4 because of this. Okay, so then let's look at what I got. So then what I have is that 2n squared minus n cubed divided by n plus 6. This is less. N cubed over 2 minus n cubed is minus n cubed over 2. So minus n cubed over 2 divided by n plus 6. All right. So let's see. Okay, so this is still a cubic expression, so it's not really going to be easy to, the inequality with cubic expression is not going to be easy to solve. I have to try to simplify further. And to simplify further, I probably want to get rid of something in the denominator because numerator is already pretty simple. So what if I drop 6? If I drop 6, I'm going to make denominator larger, denominator smaller. And then if I'm dividing a negative number by something smaller, I'm making this negative number even bigger, even more negative. So if I drop 6, I'm moving in the wrong direction. So rather than making denominator smaller, I should make it bigger, because if I make it bigger, then the number by which I'm dividing is bigger, and so the ratio is going to be less negative. And less negative will move me in the right direction. And so what I'm going to do, I'm simply going to replace 6 by n. So this would be less than n cubed minus n cubed divided by 2, n plus n, as long as n is greater than 6, right? Because n is an increasing index, so at some point this is going to be larger than 6, and I can replace n by 6. I'm going to make my expression smaller in absolute value, less negative, so inequality moves in the right direction. So this first inequality is valid as long as n is greater than 4. The second inequality is valid as long as n is greater than 6. So if n is greater than 6, it's automatically greater than 4. So therefore, if n is bigger than 6, then 2n squared minus n cubed divided by n plus 6. Now this is going to be less than minus n cubed over 2 divided by 2n, which in turn is going to be equal to, if I simplify, minus n squared divided by 4. Okay? And so what I'm going to do with that, I'm going to make minus n squared divided by 4. I'll make that less than m. And if I make it less than m and I solve for n, now it's easy to solve for n, then n squared should be less than minus 4m, or, which is the same thing, n should be greater than square root of minus 4m. Well, we cannot take really a square root of a negative number, but in this case, remember that I assume that m must be less than 0. If m must be less than 0, then minus m is positive, so this makes sense, right? So this works. Because m is less than 0. Okay, so for everything to work, then I have two inequalities. I have inequality number 1, n must be bigger than minus 4m, square root of minus 4m. And I also want n to be bigger than 6, because only if n is bigger than 6, then the computation that I did are going to work. Well, so then I'll make capital N to be a maximum of these two numbers. So it's maximum of 6 and square root of minus 4m. Okay, so then if n is bigger than capital N, then n is greater than 6, and n is greater than minus square root of minus 4m. If this is true, then this is true, then this is true, because n is bigger than 6, and then just following all inequalities that I have written here backwards, we have that 2n squared minus n cubed over n plus 6, this is going to be less than m, and that's precisely what I wanted to show. So once again, because capital N is a maximum of 6 and square root of minus 4m, then because n is bigger than capital N implies n bigger than 6, then all of this should be true. And then because n is bigger than minus square root of minus 4m, then this is true. And so my original expression is less than m, and we're done. So the limit is equal to minus infinity. And I'm going to conclude, actually let me produce a different lecture. We're going to conclude this section with two additional theorems establishing properties of infinite limits.